Okay, number 27 is an interesting problem, and we did not do one like this in your notes. So if you had a question on this, don't feel bad about that at all. Here, they're kind of giving you some information that we would normally kind of deduce at the end of a problem, and they're not giving you stuff I normally would give you at the beginning. So a ball is being tossed in the air vertically from ground level, and it returns to Earth 4 seconds later. So not a real complicated diagram. Object goes up, and then object comes down, and if we know anything about physics right here, guys, we know that this graph we just drew is a parabola, even though I drew it definitely slanted. I should probably fix that a little bit. That was kind of ugly. Back to where I was. Hang on a second. Whoop, whoop, whoop. There we go. There we go. Let's undo that graph. Okay, never mind. We'll just live with that. So what's going on right here, guys? If we're looking at a graph here of time on that spot right here, and then height is what we're looking for. So you could do S of t for position, but I'm going to go with H of t for that. We know that this thing launches at t equals 0, and now they're telling us it comes back down at a time value of 4. Now to do this problem, we're going to need something that we put in our notes here from section 3.4, and that's the book's little formula for how to build a position function. So a position function is found by taking S naught, which is your initial position, and then adding to that V naught, your initial velocity, multiplied by time, and then adding to that a 0.5 times a naught acceleration, and then t squared right there. Those three terms are the only things that are going to go into figuring your object's position. So let's think about what we know right here, guys. S of t is equal to, well, the first thing we have here is S naught, or actually, since I used H right here, probably should have thought of it as H naught. But the important thing here, guys, is that they're telling us that we are launching this object from ground level, and that means that S naught here is going to be a big old 0 that we can just ignore. Plus, V naught would be the initial velocity. That's one of the first things they're asking me to find. So it doesn't surprise me now that we don't know what V naught is. Now, t is our independent variable right there, so I'm not looking to put a value in for that just yet. And now something important happens next, guys. The object, if you read carefully, returns to Earth. Okay, that's important. They are telling us that we are on Earth here for this problem, and that means that we know what the acceleration due to gravity is in this setting. Now, you'll notice, I read the problem twice, they did not ask specifically about meters or feet or anything like that, so you can use whatever units you prefer. You guys know that I like feet better, so I'm going to go with, remember that A naught on Earth here, everybody, is a negative 32 feet per second squared. And when we multiply that by 0.5, we're going to see a term we very often see in these free fall problems, minus 16t squared. That 16 is the product of the 0.5 and the negative 32, so we end up with that. Okay, so that's where we're at. And what we're going to take advantage of is the fact that right here, guys, we actually know two important things. We know that the time value when the object comes back to Earth is 4, and we know that its height is 0. So h of 4 has to equal 0. We're going to use that information right here. So let me go with that, h. The time value we know is 4. That's going to get us, I don't need to worry about that 0 right there, V naught, which is still unknown, times this time value here of 4, minus 16 times the same time value of 4 squared. And now, let's finish that sentence now. We know that at t equals 4, our height is 0. So there's the equation that we have here, guys, and there's really only one unknown in it. We've got a 4 V naught minus the 4 squared is 16 times 16 is 256, and all of that equals 0. So a 4 V naught will equal a positive 256, and we'll divide both sides by 4 there and get, 64, I think is what we have there. Now, in order for me to answer this question correctly, I should be specific about what my units are. Since I chose to go with negative 32, and of course that was feet per second squared for my acceleration due to gravity, that means that this initial velocity here is going to be measured in feet per second. Okay, so that's what we have right here for the first answer. They asked for the initial velocity, and we've got that for them right here, 64 feet per second. They also wanted the maximum height of the ball. They want to know where this thing gets to way up here at its apex. Okay, so with that in mind, I want to take advantage of the fact, and guys, by the way, I know a lot of you are going to be tempted to say, this parabola is symmetric, and so this height occurs right here at t equals 2. Okay, look, you're right, but I don't want you guys to get in the habit of making that assumption. So what I'm going to do is pretend I didn't know that, and let's go ahead now and try to develop our velocity function and set that equal to 0. So before we do anything else, let's go back now and rewrite our position function, h of t, which I'm kind of building that off of what we had right there. So here we go. Don't need to worry about that 0. We know now, what we didn't know before, that V naught is 64. So that first term is going to be 64t and then minus a 16t squared at the end of all that. Velocity then, V of t, is going to be the derivative of that position function. And that's going to get us nice and easy, a 64 minus 32t. And again, we want to focus on the idea. Let me bring this graph, not that. Let me bring this graph down here, everybody, so we can see it a little better. We want to focus on the idea that at the apex right here, when this ball reaches its maximum height, we know that our velocity is equal to 0. So I'm going to take that velocity function right there, set it equal to 0, and solve. And again, I know you guys know where this is going. I'll bring the 32t to the other side and get 64 is equal to 32t, divide by 32, and get t equals 2. Now again, the question was, if I remember this right, what is the object's maximum height? Yeah, fine, that's it. Find the maximum height. So now we're going to go back to the h of t function right here, but evaluate it at this value of time, h of 2. So that'll be 64 times 2 minus 16 times 2 squared. And I just want to point out something that you miss if you just dump all this right into a calculator. Check this out. 64 times 2 is going to be 128 minus 2 squared is 4. 4 times 16 is 64. What do you notice about these two terms, guys? That 64 is exactly half of 128. That will happen at the apex, the peak, the vertex of any quadratic function, of any parabola. So 128 minus 64 is going to get us 64 feet now for the maximum height of that particular object. So that would be, what would I call that, guys? H max, to go ahead now and answer the question that they asked right there. And those are the two things that they wanted in this problem, guys. We had our initial velocity right there of 64 feet per second and a max height of 64 feet. All right, and that's number 27 here in section 3.4.